Here's a second hypothetical discussion, and this should say this is a hypothetical 2 to the 3 minus 1 factorial, fractional factorial. What I'm talking about is a scenario. This kind of notation says that we have 3 factors, and this minus 1 business says that it's going to be a half fraction. Okay, that is 1/2 is 2 to the minus first power. It's going to be a half fraction, and in fact there's going to then not be 8 combinations that we're going to be talking about looking at, but rather only 4. For sake of argument, let's suppose that for the full factorial, I have this set of alphas, betas, gammas, alpha betas, alpha gammas, beta gammas, and alpha beta gammas. That is, I'm doing a hypothetical analysis here, and let's just suppose that these are the main effects interactions for my hypothetical example. What that would then give me would be these values of responses. That is, if you add together main effects, 2-factor interactions, 3-factor interactions, and grand mean, you will get those 8 different means. What I want to think about is a fractional factorial situation where I don't collect data from all 8 of those corners, but only from this corner, this one, and that one. Now, as it turns out, that is a good way to choose 4 out of 8 corners. As a preliminary way of understanding that, you might look at that picture and think to yourself, what happens if I collapse this picture, say, left to right? If I take the left face and smash it into the right face and smash it into the left face, if in fact the left face and the right face, there was really not much difference in them, I would have myself a full factorial in factors B and C. That is, this picture says that if I collapse left to right, I'd have a full factorial in B and C. If I collapse top to bottom, I'll have a full factorial in A and C. If I collapse front to back, I get a full factorial in A and B. So a virtue of this thing is that it has a nice, is nice and symmetric. So this choice of 4 of 8 corners is nicely symmetric. And it has some other good properties that we'll talk about here as we go along. Let's suppose also that, well, okay, let's suppose that I get data from the 4 circled corners, and I want to think about what could I learn from data from those 4 circled corners. In particular, what about trying to get a handle on the A main effect, having data only from 4 out of 8 of those corners? What I might try to do is to say main effects are face averages minus grand average. I don't have any complete face here, but I might try to take this guy and this guy. Those are the responses on the right face that would correspond to the high level of A. Those are the ones that I have. I don't have anything else. I don't have the 14 and the 12, so I don't imagine that I know those values. But I might take the check mark guys and say average them. So I might take half of check mark plus check mark and then subtract the values for the average of those two guys and those two guys. So I might subtract a fourth of the corners that I do have. That is, I might try as a way to get at an A main effect. I'd say to myself that the real main effect is a right face average minus a grand average. I've set this thing up so that this value for the A main effect is 3. So I've set things up so this guy is 3. And now what happens if I take this computation? Well, as if by magic, if I take the two corners that I do have on the right face and average their responses and subtract the average of the 4 corners that I do have, what I wind up with is 13 minus 10. I wind up with 3. That looks like magic. What I've done is managed to learn about the A main effect, having only 4 out of 8 corners from that picture. That is, I've computed something that I've called not alpha 2 but alpha 2 star that is, in this case, it turns out to be exactly equal to alpha 2. Looks like I've gotten something for nothing here. I've only paid for 4 out of 8 corners, and I have managed to learn what's the A main effect. Before I get too excited about that, though, let's try that same calculation for not the A main effect, but the C main effect. So I would be talking about coming over here and taking the two guys on the back face that I know, the 18 and the 10, and subtracting, taking their average, so that's 18 and 10 average to 14, and then subtract the grand average, and that gets me 14 minus 10 is 4, but, so that's what I've just done here. I've gotten a sort of half fraction version of the C main effect. It's 4, but now that's not so happy because I started with the C main effect being not 4 but 2. That's how I set up this little example. Okay, so I wound up with this guy not being equal to the C main effect. That is, the half fraction version didn't turn out to be the same as the real one, the one that I'm really interested in. That might puzzle me for a while, but what turns out to be the case is this, that the half fraction version of the A main effect is the A main effect plus the BC two-factor interaction. And because when I set this problem up, I set the BC two-factor interaction down here equal to 0, then in my calculation, if this guy is 0, then this fellow and that fellow are the same. But in contrast, I did not set the AB two-factor interaction to 0. That is, the AB two-factor interaction in the way I set the problem up was equal to 2, and so I don't end up having these two guys be the same. They're not the same because this guy is 2. The general story here is that these are the things that I can know. So these can be known from a half fraction. And the rest of these, and I can't know this or this individually. All I can know is them plus another term. That's called confounding or aliasing, or I will call it ambiguity, and that comes of necessity with the use of just a fraction of the factorial. Okay, so that's general motivation here.